All right. All right, everyone. Good afternoon. Thanks for joining us here at the Smart Hub. We are happy to be here. I'm Ian Wing. I'm a manager in Deloitte's supply chain and operations practice. And this is Joe Sheeby, my colleague. We're together going to be presenting our work on digital thread, which we did in partnership with Siemens. So happy to be here and have the opportunity to present to you all. All right, so what is the digital thread? We as consultants have the privilege to go out and interact with the community quite a bit and talk to folks about digital thread and what it means to them. And what we found is that folks grasp at this concept of digital thread, but everyone's got a slightly different definition, right? And it includes all these things in the word cloud here, from FEA and machine control and inspection and all this. And it's sort of nebulously tied together. So what we wanted to do was make that real, right, and create an actual product that provided a seamless end-to-end data link from part ideation all the way through production to part performance in the field, and then from there, sort of allow organizations to scale up their additive manufacturing capabilities and deploy this type of system globally. So we've organized our digital thread into 4 phases, the first of which is scan, design, analyze, which is where the part is actually ideated or scanned from an existing part. The second phase is build and monitor, where the parts are actually produced. This is where the additive manufacturing process takes place. Moving on, after production is complete, prior to the part leaving the factory, we have some inspection operations that take place, and then finally on the deliver and manage. So that's the phase where we're talking mostly about how, I'll just roll with it. How these parts actually perform in the field and the way that they're being used in the market. All right, so. And on this journey of the digital thread, we sort of found early on in our process that a lot of the capabilities that would need to be included in digital thread were already out there in the market. So FEA solutions are available, inspection methodologies are there. There's some in-situ monitoring capability out there, but we're looking for that to continue to mature. But really what we did and the value in what we produce is the way that this is all very tightly integrated together. So this lives in the Amazon cloud. It is a always on, always connected set of technologies that work together to provide this end-to-end link, and that's what we see in the IT infrastructure layer down there on the bottom, which sort of connects all this stuff together. That's the glue that binds this system together. All right. So when we go and we talk to new audiences about this, we like to use a case study. Right. So our case study in this situation is a grounded aircraft in a remote environment that we would like to get that asset back up and moving again and get it off the runway and put it back in service. Right. That directly affects the bottom line, and we want to make sure that our customers can harness that capability to dramatically reduce the amount of time it takes to get those repairs done and guarantee the quality of the replacement parts. So our goals in doing this are just improved asset uptime. We want to increase the responsiveness of the supply chain and ultimately help our clients increase their revenue as they implement digital thread. So our test case for this scenario is a landing gear assembly on that grounded aircraft. In our hypothetical, we've got a bell crank part that's highlighted in yellow. That is broken and needs replacement. So knowing that, we can, knowing what the part is, and that it's beyond reverse engineering, it's beyond repair. There is normal maintenance that would go on in Conus, but we're thousands of miles away, and we've got no inventory on hand to effect the repair. So. We then transition that to the acquisition community. We will, and in our scenario, we find that a replacement part is not available. So the supplier is no longer in business and generating another another replacement part could take potentially months. All right. So enter digital thread. All right. So this is where we are right now. We are looking at months to field a new part, and we would like to dramatically reduce that. So with our digital thread implementation, we're going to first take that down to weeks, and then take it down to days. So Joe is going to talk us through the mechanics of our digital thread product and go through a quick demo to show this audience what we've been up to. So thank you, Joe.
Cool. All right, thanks, Ian. So just as an anchor point to where we were at in the digital thread, so again, those are the 4 phases. So we're going to step through first the scan, design, and analyze phase. So talking about how we get from a scan, in our case, of a physical part that exists that we need to reverse engineer, and walking all the way through the design portion of that, all the way through, in this particular phase, the build tray configuration. So continuing this example, just to walk through our scenario a little bit further, in Team Center now, an individual could search for parts on our as-maintained aircrafts within the system to understand where this part exists in our current fleet. So in this case, they find an active aircraft that has this bell crank that they can remove to then scan and produce a point cloud for that bell crank, put that bell crank back on the same asset that it came from, and then that point cloud can be sent to a design engineering group to be able to begin the reverse engineering process. That's really where our data for our digital model first begins, is with that point cloud that's being sent to the design engineering group. Also within the Team Center environment, engineering would search for what data exists currently for our part. So for this bell crank, the subtractive part that was in Team Center, there also were 2D drawings with PMI data, product and manufacturing information, for the bell crank that can be referenced and will be used throughout this digital thread as a reference point, both when we're qualifying the part as well as understanding certain performance characteristics of the part. So with that data in hand, we're now going to begin the reverse engineering process. So what we're showing here, just as a level set at the beginning, is ingesting that point cloud into NX and then converting that point cloud into a faceted model. So from that faceted model, we now need to create the solid model to be able to have a 3D model that we can digitally validate and then configure to our build tray. So what we're showing here, again, is that faceted model. And so during the reverse engineering process, it can often be time consuming and tedious to be able to get from that faceted model to a solid model at the very end. And so what we're showing here is some advanced functionality in the NX suite of Siemens where you can actually do something called detect primitives. So being able to detect the surface geometry off of that faceted model to automatically design that piece of it. So about 85% of the parts, so any colors on that part that aren't the light teal, were automatically detected in terms of the surface geometry there. For the remaining portions of the part where you can't automatically detect the surface geometry, they're then taking, using other advanced NX tools, actually creating cross-section curves, extruding those curves to then be able to fill in the rest of the model that we're not sure on the surface geometry for it. In addition to that, there's the sketcher functionality, which using that PMI data off of our 2D drawings, we can then actually make sure that the drawing information is being reflected in our new 3D model for this part, also using this suite. So again, the whole purpose here is to be able to use both advanced functionality and tools in combination with the data inside the digital thread to be able to more rapidly get at a finalized solid model. And so in working with the engineer that we had do this work here, he estimated that roughly 2/3 of his time was saved in terms of being able to take that scan technology, bring it into this suite, and then being able to automate some of the processes to be able to get to reverse engineering this product, greatly expedited the time it took to be able to get to a place where you can then digitally validate the model. Okay? So at this point, we now have a solid model that we've utilized the PMI data to link to it, but we want to make sure it actually functions the way we would expect it to within our higher level assembly. So what we're going to see in this is actually a motion model of that landing gear system that we showed earlier in Ian's portion of the presentation. So you see in the middle panel is going to be the landing gear system, and on the far right, we're going to show the forces that are being applied to our bell crank over a 5-second interval. So over that 5-second interval, the operation of the landing gear system is going to take place, and what we see is a peak in terms of the forces that are being applied to our bell crank. So there's an issue. There's a design change that needs to happen to our bell crank for it to be able to meet its performance requirements within the higher level assembly. And it's actually, if you caught that on the video, it's actually preventing the landing gear door from being able to fully close. There's definitely an issue that needs to be taken care of in terms of updating our design to be able to have the part that we need for our grounded aircraft. So what we're seeing here now is that from that motion model, we can then generate the loads that are on that part and store that in the digital thread, so it's then referenceable going forward, both for understanding sustainment and maintenance, but also for being able to potentially optimize the part later on, which we'll see in the digital thread. So with that load information for our part, we're now able to apply that to a finite element analysis of this part to actually understand where the stress occurs on our part and where it's failing. So you see an exaggerated version of this to make it very easy to see where the part's failing, but anywhere in red, we're seeing issues in the stress path of our part. And at this point, we would then have to go back to design and iterate on the design to be able to get us to a place where we have a part, in this case a bell crank, that actually meets its performance requirements. So once we complete that step and we'll then have a digitally validated 3D model, we can then configure that model to our build tray. So a recent addition to the Siemens suite of products is something called NX-AM, so NX Additive Manufacturing, which really helps organizations to be able to do the build tray configuration ahead of the build process. So what we're seeing here is actually a visual of an EOS M290 powder bed fusion build tray, so that's the build volume that you're seeing here. And one of the benefits of this module is really being able to manage printer-specific data. So being able to select what printers you're using, what source materials are available for those printers, what templates are already on those printers, so sort of managing all of that asset-specific data and where they exist and being able to reuse that information downstream for subsequent prints. So in our case, we have extra room in our build tray, so we're actually making a copy of that part to be able to be used for destructive testing in addition to the non-destructive testing we're going to show. And NX-AM obviously allows us to be able to actually orient our part in the appropriate way that we want to be able to get the best performance characteristics. So one thing that we're going to show here is the automation of support structures. So with some embedded technology from Materialize, we're actually showing what we're showing functionality-wise is the automation of support structure for our two bell cranks that are in the system. But there is flexibility as well to be able to update the characteristics of that support structure based upon institutional knowledge within your workforce. So what we're showing here is that we're changing our support structure to, one, reduce the beam thickness of the support structure to use less material, but also to perforate the support structure to be able to use less material and make it easier to remove that support structure after the build as well. Once you do these prints enough with these parts, you can then fold that sort of configuration, that setting or parameters into the default configuration for builds going forward. So again, it creates a way to be able to continue to build on the knowledge across your workforce. So once that's complete, this suite also integrates itself with the build processors for those manufacturers. So we're actually generating an output file for the EOS M290 powder bed fusion printer to be able to communicate those machine instructions directly to the printer for execution. So you get your CAD slices out of this, and then you also get the machine instructions that are going to drive the print for our part. Okay. So at this point in the digital thread, there's already the beginnings of the body of knowledge that's being accumulated. So we have our final 3D model that we're going to be able to do our print off of. It's been digitally validated within our motion model that can be reused and actually use real-time load information later on once you field this part. And we have a build tray configuration. So think about how you can use less labor and less lead time in the future to be able to repeat this activity once it's already in place because it's institutionalized across your workforce. So stepping into build and monitor, we're now transitioning from a place where the design engineer and the manufacturing planner have configured what this is going to look like, and now we're communicating it to the operator. So the interface that you see here is something called electronic work instructions. So the big benefit here is this is a single interface for an operator to have all the information that they need to perform their duties. So that includes step-by-step instructions of what's required. It also includes what parts and tools are necessary to be able to execute the build and the other activities. It could be relevant documentation, so attachments for deep dives on certain steps, as well as animation and visuals to be able to help understand what the in-process models of your part should look like. So in this activity that we're showing here, we have two tools that are being used. It's going to be an EOS M290 powder bed fusion printer and a wire electrical discharge machine to be able to actually remove the support structure and separate our part from the build tray at the end of this. So in this same interface, like it shows there, we have the machine instructions, again, that are available from this interface and can be routed directly to the printer for execution via Shop Floor Connect. And at a high level, the benefit here is that you have a digital process that could replace a primarily paper-based process today. So that drives greater automation and execution efficiency in terms of manufacturing operations between different manufacturing cells. But it also allows for better process control, as outputs from design engineering and the manufacturing planning organization are able to be communicated directly, and the configuration control is maintained for how that should work. And those two organizations can collaborate more easily together through automation of tasks across the different portions of the workforce. So this is actually a video of our executed build. So we partnered with the Commonwealth Center for Advanced Manufacturing in Richmond, Virginia. They were our partner agency on this to be able to execute the print. And for anyone familiar with this process, there's nothing special going on here. So we're distributing stainless steel powder for the next layer of our 2 bell cranks that are being printed. You'll see the laser centering for both part geometry and the support structure on our part. But part of the beauty of the digital thread is that as problems arise during the print process, you can more rapidly make changes to your configuration to institutionalize knowledge from both successful and unsuccessful prints. So we had an issue that arose during our first print for these parts where our support structure beam thickness was too thin. So it was causing issues where we weren't able to print successfully. We then made updates to that configuration and saved those in our digital thread so that going forward, the repeatability of being able to do this again, that's now institutionalized, and that information is made available across our enterprise to different groups that are doing the same work. Okay. Another important thing to keep in mind during the digital thread is in situ monitoring. So that could be high precision videos like we saw before of the build chamber itself. It could be infrared video trying to do thermal sensing here, or it could be image data. But all of that information gets at one of two things: either being able to figure out what settings and parameters lead to more successful prints, or what information you can glean off of your as manufactured part that can inform testing, which we'll see later. Finally, at the very end, we used a wire electrical discharge machine to be able to, again, remove that support structure, wire our holes, and actually separate the part from the build tray. Just for the sake of time, we're not going to show, there's another video as well that we did post-processing for our part using a vertical milling center machine to be able to get to our tolerance levels for our part specifically as well. So that would be a part of the build and monitor phase, is any additional post-processing that you would do for your part. So that's the end of build and monitor. So at this point, think that we have electronic work instructions for both executing a print and doing post-processing activities. So again, think reuse of that information, building on the knowledge that's already available, so less lead time and less labor hours to do it again. But we also have in situ monitoring data, and like I mentioned before, that can be used in 2 different ways. One, to inform more successful prints in the future, but also feeding that forward into test and validate, which we're going to show next. All right, so around in situ monitoring, one particular area that's relevant for metal additive manufacturing is being able to track thermal sensing data. So it's sort of monitoring the melt pool on individual layers of your print. So one idea of how this could work, utilizing some of the data that we got from our NX-AM module during the build tray configuration, is by tracking down to the rastering path on an individual layer and having sensing capabilities that can detect anomalies down to that laser position on a particular layer, you can then track that individually and be able to aggregate that information together into a solid model that then a non-destructive testing technician can reference, and that could drive what sort of resources and techniques might be used at later phases to be able to validate our part. So this is similar to how an MRI works, where you take cross sections of the human body to be able to understand internal structures, internal organs, and then aggregating that together into a solid model to be able to understand what the solid body looks like. So very similar to that. And not only could it help inform inspection, but later on down the road, as you continue to gather more and more data, this could be a path towards a more mature digital thread validation process where you're not validating a part post-build, but instead you move towards validating a process post-build, which has its own benefits of greater automation and process efficiencies in that as well. So this is a visual of what that could look like, of aggregating that thermal sensing data together into a solid model. And what you're going to see on the bottom right-hand corner of the bell crank is a red blotch of in situ monitoring data on this model where thermal anomalies occurred on our part. And so you can take the non-destructive testing technician could take a cross-section of this part to be able to see the relative depth of where anomalies occur in the internal geometries. And that can help guide, again, what techniques or resources might be deployed to be able to validate this part. Okay? So we're going to see that here as they take a cross-section of the part and do a little overhead to be able to see, again, on our particular area, there are anomalies up to the surface of the part, but there are also anomalies within the interior of the part as well. So the whole idea is trying to validate that those won't affect the performance of our part as it was manufactured once it goes into the field. So for the purposes of our digital thread, we're going to show two types of inspections that could occur. Not saying that these are the only ones that would need to occur, but trying to show the type of data that you can collect along the digital thread and how it can be used to inform future certification processes. So here, we're showing two types of inspections. One is a coordinate measurement machine, and the other is an optical scanner. So for the coordinate measurement machine, we're talking about a probe that's going to check high priority areas of the part for both its measurement as well as its surface finish. And it's actually automated based upon the PMI data linked to our 3D model. And so again, so that's under configuration control and actually can be automated in terms of the path from NXCMM. But beyond automating that probe path, you can actually use the information off of your in situ monitoring data to change the priority areas of your part that you might want to inspect to prioritize more areas in that bottom right hand corner, like where we saw where the red areas were on our 3D model. So once that operation runs, and again, this interface also allows you to take the machine instructions and route it directly to the CMM for execution. Once it does run, there's also direct integration into Team Center for a non-destructive testing technician to easily look at this report and validate that all of the tolerance requirements were met, which we'll see in a second. So the report comes up, we're able to validate that all of the different tolerance levels were met on our part. Okay, so that's the CMM. You could also do an optical scan for your part as well. And for this optical scan, we scan our as manufactured part to produce a point cloud, convert that point cloud to a solid model, and then you actually layer both your as manufactured model over your as designed model to be able to check the variations between the two. So by setting those to different colors and then actually setting the accuracy or tolerance level between those two models, you can validate whether or not the variations are too significant to be able to validate this part or not. And so as we see here, there is variation that we'd expect to see, but the variation is within tolerance for our particular part that we need to field to get our grounded aircraft back out of that remote environment. So at this point in the digital thread, the data has been gathered to be able to reach a fielding decision for our part, and based upon the data that was gathered again along the digital thread. And this becomes information that can be reused in terms of what data is required to make what decisions going forward. So the big benefit from test and validate is really being able to understand exactly what data is required to make what decisions, really accelerating the time it takes to certify a future part that might be the same part or similar parts using the same or similar machines going forward. So again, think about being able to institutionalize that knowledge and reuse the data that's available. But we also understand our as manufactured part at a unique level of detail, and that could actually drive unique maintenance or sustainment decisions we might make for our particular part because we understand the way it performs because of how it was manufactured. And last, of course, for auditability and quality assurance purposes, we also know, again, what decisions were made using what data, and that can be referenced if quality incidents do come up for this part. All right, so going into deliver and manage, this is traditionally where the process stops in terms of a PLM software type component. Usually a different system might track inspection reports or maintenance reports in the system, but we're recommending to continue that progress so that you can then get performance and usage data about that part in particular to maintain the digital twin through its usable life. So the idea here is that you can then, once that part is installed on your as maintained aircraft, continue to tag data against it and itemize it down to the level of detail that you link an inspection or a maintenance report against that part. And that allows you to track any sort of quality incidents that showed up for that part, as well as being able to see the history of part movement. So where it's been installed on different tail numbers, as well as its in-service versus out-of-service status. And not only does that give you a more accurate digital twin of your part, but rolling that up, it really gives you a more accurate digital twin of your asset that's in the field. So being able to actually understand your as-maintained assets that you have out in the field. And of course, this could accelerate to being a much more advanced functionality if you do deploy sensors that are on your assets and actually do some sort of real-time capture of performance and usage data as well. All right, so I know that was a lot of data that was accumulated along that entire first round of the digital thread. So much knowledge was accumulated and fed forward in the process, and that there is a significant value driver for that. So Ian mentioned that before in terms of the benefit that we see of being able to shrink the cycle time to field a part by collecting all this data. But the real value comes in being able to reuse that data and build upon that intelligence to be able to have a blueprint for the next print. And so that's why we say that there's not just that first benefit of just having more automation, better knowledge sharing, better collaboration, but really being able to apply the body of knowledge helps squeeze that, or helps compress that time it takes to field a part even further by really reusing that and making it something that's accessible to the workforce that's going to be doing this work in multiple locations across your organization. Okay, so that describes how data-driven insights could lead to process optimization for AM in your organization. But Ian's now going to come back and talk to us about how data-driven insights can lead to product optimization as well.
Sure, thanks, Joe. All right, so we've gone through this process. We've collected a variety of different modalities, quantities, and types of data throughout this process. We've seen design data, we've seen inspection data, we've seen performance data. The value in what we've produced here is that all this stuff is that was once point solutions is now integrated together tightly in a singular, always-on information system that allows us to act on that and create insights through this physical to digital to physical loop, right? So the first step in this, which we've described thus far, is getting that data digitized and into the system, right? So we're capturing these, signals and data from the real world, codifying it from different sources, and putting it all up in our platform, which, by the way, can be accessed anywhere in the world by anyone with an internet connection, based on rules and permissions, of course. You wouldn't want everyone to see the same types of data, but it's all up there, and it can be pulled down selectively or as a whole by any authorized user at any point, right? The digital to digital loop is the next step in that process. That's where we apply analytics and things like machine learning to understand what's going on throughout the design process, through the fielding of the part, and leveraging all that performance data to make some informed decisions. And then the final step is the digital back to physical transformation, where we take the tools that the lessons that we've learned from analyzing the data and apply it to the next iteration of parts. So what does that look like? So a practical example of this is from our motion analysis study before that Joe showed. We showed the part failing, basically. The door wouldn't close all the way. So we need to effect a redesign of that part, right? And that's an example of a specific insight from the digital thread being put into action. So what we see here is we're going to do a topology optimization of this part. We're going to constrain the geometry and have these endpoints on the part. We're going to input some more parameters, including the load case that we got from our simulation. So that's being entered now. Just my luck with this thing. Every time I get up here, it starts going again. But anyway, so what we'll see here is we'll see the optimization taking place. Again, topology optimization is not new by itself. However, what we're showing is a tighter integration of all these components of the product lifecycle than what we've seen before from other sources. So we'll run our optimization here, and we will see we have this optimized looking shape. This is the classic organic looking shape that you see from something like topology optimization. And we'll see that once we run our finite element analysis again, we're able to see that the part actually performs much better than the original design with less material, less mass, and less volume overall. So leveraging the digital thread, we are able to identify those specific instances for improvement. Identify which situations we want to apply these techniques in, and then actually do it all in the same interface. The same singular system is running all of this. All right, so what are we doing with the digital thread? To close it out and wrap it all up, we are designing anywhere, we're building anywhere, and we are sustaining anywhere. All the while we're doing this, we're capturing and codifying that knowledge that exists at present in different information systems all over the globe, tying it all together, accelerating that learning process. So one of the challenges that we've had with Additive so far is that there's just not a breadth of data to qualify against and to build confidence in the parts that we're producing. Whereas traditional manufacturing, we have the benefit of thousands of years of metallurgy, right? That says that, hey, this steel ingot is good. right? We know this because we've been doing it this way for, decades, or if not hundreds of years. With additive, this digital thread will allow us to dramatically accelerate that learning process and build confidence in the results of the additive manufactured parts that folks are producing these days. So we'll be able to improve our process, and then finally, we will facilitate a shift from physical inventory to digital inventory. We'll be shipping electrons back and forth across networks instead of moving finished goods across oceans and continents. So we see a lot of potential here, and we are happy to continue the conversation with folks and continue to explore this together. So we've built a prototype, and we're looking forward to operationalizing this with some other folks going forward. So with that, we will pause for a moment and take any questions. Questions from the group? Nobody? The group this morning had like 3 or 4.
We should have had feelers in there.
Why does Deloitte care about additive manufacturing was a popular one. That's always a popular one.
They can't believe it. Yeah.
I guess we can. Good question. Thank you for asking. So we Deloitte have a long history of helping our clients understand new technologies and the business implications thereof. So with additive, we see a major change coming in the way that we manufacture goods, and we are there to help our clients work through the business challenges of that and provide some of the solutions like digital thread, which helps sort of institutionalize and scale up these technologies. Taking advantage of AI into the and integrating that into DTAM. So I think that we're waiting for that technology to continue to evolve a little bit. We put it in here as an illustrative case of something that we could do. I think that applying machine learning and AI to this database that we have will definitely yield results. It's hard to say exactly what they'll look like at this point, but I think that once some of the optimization algorithms get smarter for part design, we'll be able to quickly identify those opportunities to apply it. Close enough? Okay, good. Anything else? All right, well, thank you very much, guys. We appreciate the opportunity to come and share this with you. This has been a fun journey to be on with Siemens, and we're looking forward to next steps.
Cool. Thank you. All right.